today is Steve Kivelson from Stanford. When you look at the web, you get all sorts of weird things. Like the APS has him listed as he graduated from Hillendale Nursery,
which is correct.
Sometime later, received his PhD in physics from Harvard. So in between that time, I actually knew him when he was a high school student. I always thought he was a bright kid. I still think he's a bright kid, because his parents were at UCLA when I was there. He did get his undergraduate and graduate from Harvard. He was then a postdoc at Santa Barbara, at Penn in Santa Barbara at the Schrieffer. He was then for many years a faculty member at UCLA, and now he's at Stanford. He won one of the highest awards in superconductivity, the Bardeen Prize, and he's worked in correlated electron systems. He discovered pneumatic phases of electrons. He looked at fluctuations in superconductors, and he's going to tell us today about how superconductors.
Thank you very much. Some years ago, maybe it was 10 or 15 years ago, I was invited to be the, the color speaker at a Gordon conference on soft condensed matter physics. And I was supposed to give a talk on all of hard condensed matter physics. And Paul was the speaker after me, and or maybe it was before, I don't remember the order. But at any rate, I spent a lot of time explaining why the questions I was talking about were so deep and so difficult. And Paul asked, yeah, but are you going to be talking about exactly the same thing in 10 years? And well, the answer is yes, but I'd like to convince you that first, that's because these are deep and interesting questions, but second place, we are making progress. It may not be super fast, but on the other hand, yesterday there was an interesting talk on the fundamentals of quantum mechanics. So at least some people here, I think, are willing to talk about problems that have been interesting for research for more than a few years. So what I'm going to do is give you something of a progress report on where we are in the theory of high temperature superconductivity, and and the forward doesn't seem to work. Okay, good. Good. Much of what I'm going to tell you is summarized in this paper, which recently was published in Nature. I'm very proud of this paper. It's not actually all that much of an intellectual accomplishment. But as an accomplishment in diplomacy, it was quite remarkable. This is a group of people, all of whom have been thinking about this problem for the last 30 years from very different viewpoints. And the fact that there was actually a lot of things that we could agree upon was, I think, quite interesting. So here's a schematic phase diagram of a cuprate high temperature superconductor. This is what we're going to be dealing with. There's an antiferromagnetic phase over here. I should tell you what the axes are. This is temperature. This is chemical doping. It's changing the concentration of something in the chemical makeup of the material. There's an antiferromagnetic phase sitting over here, which at least for y = 0 is insulating. And there's this high temperature superconducting phase here that occurs in a range of doping close to the antiferromagnetism. And one of the things that has emerged in the last decade or two is that there's a lot of other things going on in this phase diagram. There's a highly anomalous normal phase. There's a pseudo-gap regime that now has been characterized as having tendencies to various sorts of other broken symmetries, electron nematic order, charge density wave order, spin glass order, and maybe others. So this is the general description of the phenomena that we're going to be talking about. By the way, feel free to interrupt with questions. If I don't get through the entire talk, that's fine. So there are some things that we've known about.
Electron nematic order?
What?
What's electron nematic order?
I'll describe that. Some things have been long established. One is that high temperature superconductivity, like conventional superconductivity, involves the condensation of a charged 2e complex scalar field. That's the order parameter theory. The pair field has an unusual d-wave symmetry, and that brings in some new fundamental pieces of physics. In particular, at low temperature, there are gapless nodal quasi-particle excitations. So the low energy physics is distinct from that of conventional superconductors. And as I already mentioned, the superconducting phase is proximate to an antiferromagnetic phase, and the influence of this phase can be detected throughout the whole interesting range of dopings. There are a number of other things that are more detailed that I won't mention here. What are the big questions that we would really like to answer and we've spent the last few decades struggling with? Well, the first and most obvious is, what is the mechanism of high temperature superconductivity? And in particular, why is the transition temperature high? And why is it associated with magnetism? What gives rise to the complexity of the phase diagram? Why are there so many regimes and ordering tendencies seen in these materials? How can we understand the normal or bad metal state of these high temperature superconductors, but many similar anomalies seem to be common to a large class of highly correlated materials. Normal states where the normal theory of metals, the Fermi liquid theory of metals, fails miserably, and where we therefore need some new theoretical framework for understanding the behavior. And do exotic phases of matter play a role in the physics? That is to say, is it just new regimes of familiar phases of matter, or are there actually new exotic phases, fractionalized phases, spin liquid phases that somehow play a role in the physics here? I thought it's interesting to note some things that are generally not considered important, which may be wrong. So one thing that's not considered important in the field is the role of quench disorder in the physics of these materials. And there's a strong reason for this, which is that much of the effort in this field over since they were first discovered, has been focused on trying to get better and better and more crystalline and more pure materials so we could somehow get at the essence of the problem. And in fact, a lot of the progress in the field has come from just this progress in material science. We have much better characterized materials, and so the experimental facts, many of the experimental facts, are no longer under dispute. That does not necessarily mean that disorder plays no role. A second thing that here, in particular, one might worry about is what is the role of non-equilibrium and or slow dynamical processes on the physics. As far as I know, nobody has paid any attention to this question, but it's not obvious, especially once one starts thinking about the role of disorder. why that should be. Yes?
What does slow mean?
Slow means that it's slow enough that on laboratory timescales, the system maybe hasn't reached equilibrium, so that maybe we're not always looking at the question, I guess, that's behind that is, should we be understanding everything we see in terms of equilibrium, statistical mechanics, or do we have to worry about glassiness or some other form of non-equilibrium effects? And, okay, I'm going to mention a little bit the role of disorder, but neglecting these isn't stupid. It may not be right, but it's certainly not stupid. That somehow or other, what we would really like to understand is that even if these materials have some disorder, and even if not all of the degrees of freedom are always in equilibrium, in order to understand, what we would like to do is imagine extrapolating to some ideal problem in which disorder maybe is missing and some structural complexities are missing, maybe phonons are missing, whatever the unimportant degrees of freedom are. But even if this is the case, in interpreting the experiments, we may be forced to deal with some real-world problems like what are the roles of disorder. Okay, so I'm going to spend most of the time, maybe at least half of this talk, talking about the mechanism of superconductivity, because here I think we actually basically know the answers. So superconductivity involves pairing of electrons, and the basic problem is that at a microscopic level, electrons repel each other. And so one needs to understand what it is that causes them to pair, given that they repel each other. And in the conventional superconductors, we understand the basic principle that's involved. It comes from the retardation of the phonon dynamics, that even though the induced attractive interaction is probably weaker than the bare repulsive interaction, because the induced attraction is retarded, it can overcome the stronger bare repulsive interaction. And so as long as this hierarchy of scales, that the Fermi energy is large compared to the phonon frequencies, which are in turn large compared to Tc, we have a moderately well-controlled theoretical understanding of how conventional superconductivity arises. Because we're dealing with an induced attraction, and because the induced attraction is generally fairly local in real space, conventional superconductors are mostly simple S-wave in their character. Already here, there's a puzzle. It was long understood that in order to find superconductivity, one should stay as far away from magnetism as possible, because magnetism comes from strong effective repulsion between electrons. And so if superconductivity comes from attractive interactions between electrons, you would like to stay away from magnetism. And indeed, this was one of the famous Matthias's rules of where to look for superconductors. Okay, so the new feature...
Magnetism, you mean not only ferromagnetism?
I mean not only ferromagnetism, antiferromagnetism, all of these things come from... I mean, you have to basically polarize the spins locally, and that's somehow due to repulsive interactions. It's two electrons of the same spin not wanting to be at the same place. So unconventional superconductivity arises directly from the repulsive interactions between the electrons, and rather than running off of the frequency dependence of the effective interactions, it runs off strong K dependence of the effective interactions. So let me try to explain this, and I'm going to do this explicitly. I'm going to write down some equations. I hope they're familiar equations. They're at least simple equations to just see how strong K-dependent repulsion can give rise to unconventional superconductivity. And I'm going to, without apology, be writing down BCS mean field equations. I don't want you to think that in any sense this is an accurate representation of the physics of, say, yttrium, barium, copper oxide, some particular high-temperature superconductor. I want to illustrate the way in which strong K-dependence repulsions lead to unconventional superconductivity. So this is a conceptual introduction to the problem. So this is the famous BCS gap equation. Delta is the K-dependent BCS gap. V is the effective interaction in the Cooper channel. This is the interaction, that scatters a pair of electrons from Q and minus Q to K and minus K. And E is the quasi-particle dispersion. And this equation can easily be integrated perpendicular to the Fermi surface. So we'll focus on K's near the Fermi surface. And so we'll get a gap equation of this form.
And Q is running
over the Fermi surface here. So I'm taking delta on the Fermi surface. So K hat and Q hat refer to wave vectors on the Fermi surface. And this is nothing but the BCS log. And I've just kept the angle dependence of things. In the S-wave case, this would be a constant, so we would have done the full integral over K space. Here, I've kept an angular integral, an integral over the Fermi surface. But other than that, there's nothing unconventional I've done here. And now, what one can see is that this becomes an eigenvalue problem. I define this, dimensionless effective interaction, which is V divided by the average Fermi velocity. And we find eigenstates of this. We find the eigenvalue lambda with the biggest positive value, and that gives me the gap is the cutoff times e to the minus that eigenvalue times whatever this eigenfunction is. If you prefer, in thinking about BCS gap equation, you can think about a one-loop RG treatment for the effective interactions, which would give you the same result. Okay, now, so I want to look at what the solution of this problem looks like. And for simplicity, let's imagine that there are sort of two pieces of Fermi surface that are important, or two Fermi surfaces that are important, two patches, two values of K and K prime. And we'll imagine that U has some value called U small if we're scattering between vectors that are part of the same patch of Fermi surface, and some other value called U large, which is what we get for scattering between pieces of the Fermi surface that differ by a large amount of momentum. And now, we all know how to diagonalize 2 by 2 matrices. And so in particular, even if U is positive, so that is to say, even if I have only repulsive interactions, so long as U large is bigger than U small, then this effective interaction is attractive. Lambda will be positive, but the other consequences is that the eigenvalue, the eigenvector is a sign-changing eigenvector that's plus on one piece of the Fermi surface and minus on the other. So we get unconventional superconductivity when the repulsive interaction at large momentum transfer is larger than the repulsive interaction at small momentum transfer, and an inevitable consequence of that is that we have a superconducting gap that changes signs on different parts of the Fermi surface. this was in the context of a mean field theory. There are many ways one can try to do something more responsible with this. The calculation I understand best, because it's one I did. I only understand calculations I do. Not necessarily the first or not necessarily the one you'll like best. But what we did was we asked, could we understand this thing in a theoretically responsible way in any limit? And the limit it can be understood is in the limit of weak repulsion. Say, take the Hubbard model with a very small value of the repulsion u, and then we can write down an asymptotically exact expression for Tc, which is some cutoff, times e to the minus 1 over lambda, and one can calculate the first two terms in the asymptotic expansion for lambda. These coefficients a and b depend only on the band structure. They're features of the non-interacting system, and this can be derived using renormalization group as an asymptotic expression.
What's Kohn-Luttinger here? What are you referring to there? There's superconductivity paper?
Yeah, they're superconductivity papers. So the renormalization group's analysis of this leads you to look more or less at the diagrams they looked at. The physics that leads to this is actually quite different from what they focused on. It has actually nothing whatsoever to do with Friedel oscillations and singularities to do with the Fermi surface. In fact, you can prove that for a circular Fermi surface in 2 dimensions, this coefficient A vanishes. So the details of this depends on band structure in some complicated way. A depends on states integrated over the whole band, but it's a cousin of the Kohn-Luttinger analysis, and it's more or less summing the renormalization group more or less sums the diagrams that they looked at. Okay, so that's the first step. And then the second step is to notice that if you have somehow short-range magnetic correlations, that's some statement about the particle-hole susceptibility, which in turn is some statement about the screened effective interaction. So if you want to get an effective interaction that's peaked at some large wave vector, the most obvious and the most well understood way to do that is by being close to a magnetic state, so there's some form of short-range antiferromagnetic correlations. And so with this sort of analysis, one can at least rationalize the nature of the unconventional superconductivity that's seen not only in the Cuprates, but in a variety of other things, just by looking at what momentum do you think the biggest repulsions are, that comes from the magnetism, and what's the structure of the Fermi surface, and from that you can make some inferences about the symmetries and character of the superconducting state, which at least more or less seem to be correct. Yes?
What is it that changes as the antiferromagnetic correlations get long range?
Long range.
Yeah, so this approach
Yeah, so
depend on the range of the correlation.
right. So there are a number of things. So one is superconductivity ultimately is an integral over the whole Fermi surface. So if the correlations get so if this interaction is very highly peaked, that's actually very inefficient. It means you only get pairing from a couple of points on the Fermi surface, a couple of hot points. So you want to have U large bigger than U small, but ideally you would like it spread out over, a large range of K. The second thing is if you actually go into an antiferromagnetically ordered state, if you go into an antiferromagnetic ordered state, you rearrange the Fermi surface. You gap out large portions of the Fermi surface and you reduce the density of particles to pair. So antiferromagnetism is for several reasons bad, but a little bit of antiferromagnetism is sort of good. Yeah.
How does one see that the superconducting temperature will be much higher?
That's a good question. So certainly within this asymptotic theory that I was boasting about, where's that? No?
We're going along the right.
Oh yeah, it was later than this. Right. So if you take a look at this, this is actually an expression for the lowest temperature superconductivity you've ever heard of. It's not only exponential in 1 over my small parameter, it's exponential in 1 over my small parameter squared. So, okay, so on the face of it, this is really bad. On the other hand, if I extrapolate this to interaction strength of order 1, then at least I have no other small parameters here. The prefactor here, since this is a purely electronic mechanism, and since this comes directly from the repulsion, then one can hope that the prefactor here is some characteristic electronic energy, not some phonon energy. So we get 1 or 2 orders of magnitude in TC just by the prefactor, even if we extrapolate all answers to lambda equals 1. Now, that's extrapolation. You might say that you think I'm not allowed to use this unless lambda is less than 10 to the minus 2. And of course, I can't argue with you, and e to the minus 100 is really bad news. So,
Yeah, no, the basic answer is that this is an electronic.
is an electronic mechanism. Exactly. And so the prefactor is bigger, and after all, if you look at how do you get anomalously high TC from a phonon mechanism, it's not by making lambda bigger. Lambda is always 1 in all of the decent electron-phonon superconductors. The ones that have the high transition temperatures are magnesium diboride and hydrogen sulfide under pressure, all things where the phonon frequency is much bigger. So making the prefactor bigger isn't an insignificant idea. Yeah, so, okay, so this brings me to what sort of standards we should use in declaring that we understand the mechanism of high temperature superconductivity. And let me first talk about conventional superconductors. I think we all agree that we understand the mechanism of superconductivity in conventional superconductors, and nonetheless, theory has had a rather inglorious record of predicting new superconductors or even quantitatively accounting for TC. There is some controversy over this, but at least I think most people will agree that this has not been a great success, and yet we don't have any doubt that we understand the mechanism of conventional superconductivity because the theory is so compelling and so internally consistent. And, well, because there are other things we can test, there are some quantitative predictions that can be made based on the theory. Most of those are predictions of mean field theory. And that's where we're going to be in worse shape here, because at least in conventional superconductors, the normal state is understood with great precision because it's a well-developed Fermi liquid with sharply defined quasiparticles. And as I mentioned in the beginning, that's not the case in the high-temperature superconductors. So I propose that the statement we understand the mechanism of high-temperature superconductivity should be accepted at a lower standard of proof than it was for conventional superconductors. That's what I just said. Now, we still can hope to address some qualitative questions like look at the band structure and predict what the symmetry of the superconducting order should be. And for instance, that was done in the iron-based superconductors moderately successfully on this sort of theoretical grounds. Okay, so
And it's always non-S wave, but it's not always E wave, is that sort of?
So actually in the iron-based superconductors even it's S wave, but it's always unconventional. That is to say, it changes sign from one piece of the Fermi surface to another. So it can do that in an S-wave way. So for instance, in the iron-based superconductors, you have multiple Fermi surfaces. You have, say, an electron pocket and a couple of hole pockets, and the sign changes as you go from the electron pocket to the hole pocket, but it's still S-wave. It's the sign change that's the sine qua non of a mechanism from repulsions.
That doesn't mean D.
What?
That does not mean D.
It doesn't mean D. In fact, it doesn't even, it can be, you can get triplet superconductivity out of this sort of mechanism. You can get S-wave. You can get F-wave. It depends on details of the Fermi surface and on the details of the interaction, but in ways that actually aren't that hard to work out. Okay, so the second striking thing about the mechanism of superconductivity is you might want to ask, why is there a superconducting dome? Why does Tc rise and then drop over a narrow range of doping? That's one of the striking things that was noticed very early on that's unlike, for instance, lead. If I alloy lead with something, it doesn't really do anything to Tc. So the zeroth order answer to this is also obvious. The superconductivity has some sort of a love-hate relation with antiferromagnetism, just along the lines that we were just discussing. If you have too much antiferromagnetism, it turns the thing into an insulator, and one thing an insulator can't be is a superconductor. But if you get too far away from the antiferromagnetism, you lose this structure of the effective repulsion, and so it wants to be close to the antiferromagnetism, but not too close. But there's a somewhat more detailed understanding that you can have, which is that the optimal Tc is actually a crossover between two regimes, and that at large doping, far from the antiferromagnet, Tc is determined by the pairing scale, just as it is in conventional superconductors. But at small x, as one approaches the antiferromagnetic insulating phase, the superfluid density gets smaller and smaller, and so ultimately the superconducting Tc is controlled not by the pairing scale, but by the superfluid stiffness. So the way to think about this is to ask a different question than we usually ask, not if I give you information about the normal state, how do I predict Tc? But how about if I tell you about the properties of the ground state of the system, the superconducting ground state of the system, and I ask you to predict Tc? That is to say, to try to estimate what is the energy scale of the fluctuations which, when they thermally proliferate, will destroy the superconducting phase. And so there are two characteristic energies you can make. One is the gap scale. That tells you about how hard it is to break apart pairs, how to take a Cooper pair, break it into two quasi-particles, and thereby deplete the condensate. And for conventional superconductors, this gap scale is always what predicts Tc. But you could also imagine making fluctuations which just twist the phase of the order parameter without necessarily breaking pairs, and the strength of that is determined by the superfluid stiffness or the superfluid density divided by some effective mass. And the Tc is going to be the minimum of these. That is to say, whenever one or the other class of thermal fluctuations proliferate, they're going to destroy the superconducting state.
What's the energy scale of rho s?
Right. Good question. So, rho s, so what I really mean by rho s is the helicity modulus, the term that multiplies kappa gradient theta squared. So now it depends on what dimension we're in. In 2 dimensions, kappa is directly a temperature. In 3 dimensions, we need a length scale here. It's kappa over some length scale that's equal to Tc. And So in the cuprates, fortunately, since they're layered materials, this length scale is just the spacing between planes, and everything's easy. If you're looking at a more three-dimensional material, probably that should be taken to be the zero temperature coherence length. And I've got the power in the wrong. There we go. It's a little more complicated in 3 dimensions in that it's not entirely determined by the superfluid density itself. But at least in many of the materials that we're going to talk about, since they're 2-dimensional, this isn't an issue. And so the superfluid density is directly a energy scale. Okay, and the point is that as we approach this mod insulating state, since the superfluid density must vanish, then ultimately this thing must control superconductivity at low enough doping. And this is, of course, a very general proposition, especially for low-density 2-dimensional systems. And so not only is there considerable data that this goes on in the cuprates, this is a sketch of the phase diagram of the cuprates showing some scale which is really a zero temperature scale. This is some sketch of what the zero temperature gap scale is. But here is for some other very low electron density, strongly correlated 2-dimensional superconductor that occurs in some heterostructure of transition metal oxides. And again, what you see is a superconducting dome where the temperature scale inferred by measuring of the zero temperature gap rises as the superconducting TC drops as the concentration of mobile carriers gets lower. So this is a very general, I mean, this TC is 100 times lower. This isn't a high temperature superconductor, but it's the same drama. Okay, so that's the answer to the first question, is I think I've told you things we do understand, both about the mechanism of pairing and about why you see a superconducting dome. The second thing I want to talk about is what gives rise to the complexity of the phase diagram. And here, mostly, I want to convince you that this is really an exciting and important problem. I'll propose some ideas of what the answer to it is, but I'm more convinced that we've identified this as a problem than that anybody has the definitive answer to it. So, and in particular, why are there so many phases, and why are they characterized by the same energy and temperature scales over a wide range of circumstances? And why do they compete with each other so ferociously? Why isn't one the dominant order and the other lives on the leavings of the dominant order parameter? Okay, and again, if you are interested in more, we've written a fairly extensive review on this topic, and we've even given it a name. We call it intertwined orders. Okay, that doesn't mean we understand it, we've just named it. So here's again another image of the phase diagram of the cuprates. And one of the things that appears, this is on this consensus paper, and the fact that it appears in this consensus paper is important. What's occurred is that the occurrence of charge density wave order in this regime is now not a speculation, and it's not controversial. It's really been established. And let me look at a little bit of that just as to illustrate the point. So, to start with, let me remind you what you expect of competing orders. That is to say, you know, if you look at the analysis in Chaikin and Lubensky, And you would find the parts on multi-critical points, and what sorts of things would you sketch? So you'd say, okay, I have two ordered phases, one A and one B, and if they didn't interact with each other, you'd have a phase diagram that looked like this. And if they interact with each other, say if they compete with each other weakly, you might have a tetracritical point and some coexistence between them, and a tetracritical point there. And you know, at any rate, over most of this phase diagram, what you see is either you have pure A or pure B, or unless you're right at this multi-critical point, you have A and then a wimpy little bit of B that just manages to eke out, but there's no competition. A is the winner here, B is the winner here. Maybe there's a region where the winner doesn't take all, but it takes most. And this isn't just a sketch, you know, here's some charge density wave material. This is CCW means commensurate CDW, commensurate charge density wave. NCCDW means not commensurate charge density wave. I don't know why they didn't call it an incommensurate charge density wave. I think they were trying to be more non-committal than that. And here's superconductivity. And so first place, this superconducting TC has been multiplied by a factor of 10 because the scales of these orders are just not the same. Why should they be? And moreover, there's no competition. You know, once the charge density wave turns on, it pretty quickly kills the superconductivity. Once the charge density wave has gone away, the superconductivity is fine. Okay? Now, that's not what happens in the cuprates. Let me show you a very dramatic example. This is one of the cleanest of the cuprates. This is oxygen-doped lanthanum. Oh, there's no S there. It's oxygen-doped lanthanum cuprate. And what you see here is the magnetic susceptibility as a function of temperature. So you see a very nice superconducting transition temperature here at 42 Kelvin. And what this is this is a neutron scattering study. This is an incommensurate spin density wave Bragg peak that's measured by neutron scattering, which turns on in a rather order parameter-like way. There are lots of puzzling things about this. Magnetism in general in the cuprates has huge fluctuation effects. Why this transition looks so mean field-like is a little bit puzzling. The correlations involved are extremely two-dimensional, but the correlation length is 400 angstroms in plane. Why it doesn't lock into a three-dimensional order is a puzzle. But the puzzle I want to focus on right now is why is it that these two different broken symmetries that seem to have nothing to do with each other have exactly the same critical temperature? That's really weird. Here's the best example of a material that has coexisting density wave and superconducting order in the cuprates. This is lanthanum barium copper oxide. This is a phase diagram as a function of barium concentration. And you can see the complexity that I was talking about. Here's the onset of charge density wave order. There's the onset of spin density wave order. Here's the superconducting TC as a function of doping. They obviously interact with each other in some very complicated way. They all have more or less the same characteristic temperature scale. But now I want you to see something, which is as I come down as a function of temperature here, although what's marked here is a very low superconducting transition temperature because that's the temperature at which the Meissner effect is first determined. If you measure the resistance in the more conducting in-plane direction as a function of temperature, you see that it has an order of magnitude drop. So it's some substantial form of two-dimensional superconductivity that onsets, notice this is called TSO, that's the onset of spin density wave order. So again, we have this coincidence of two completely unrelated broken symmetries. by the way, this is a really weird material. It becomes sort of quasi-superconducting in two directions, but remains, this resistance is in ohm centimeters. This is in the more resistive direction. So it remains, well, you can see the resistance has an insulating temperature dependence and an enormous magnitude. So this thing is something that looks almost insulating in one direction and superconducting in two others, which is, well, impossible other than the fact that it's true. Okay. Here's the beginning of the more modern inferences on this. This is YBCO, which is by general consensus the cleanest of all the high temperature superconductors. There's no particular metric of that. That's just a sociological fact. But anyway, it's accepted to be the cleanest of the high temperature superconductors. And here is a X-ray diffraction peak. This is actually an exciting new X-ray diffraction method called resonant elastic X-ray scattering, right?
Yeah.
RIX.
Well,
REX, yeah.
but you do it with the same device that you do resonant inelastic.
Right, okay, anyway, you know, Rick or John or something like that. And you see there's this nice charge ordering peak. It starts growing as you lower the temperature. Interestingly, then it reaches a maximum and starts decreasing. Here's the peak height as a function of temperature. It onsets in some very non-transition way, some crossover way, starts growing, but then it hits superconducting TC and it takes a nosedive. So these two orders are actually competing on a very equal ground. They're very comparable in strength. One can suppress the other. Here's some later data, so it's even more dramatic, how the charge density wave intensity increases and then gets quenched substantially at the superconducting TC. Within the last year, it's been discovered that if you can see that superconductivity and charge density wave order compete. So you would like, if you want to see what this charge density wave is really made of, to suppress the superconductivity. And so to do that, one goes to high magnetic fields in order to see what does the fully ordered charge density wave ground state look like. And here's what it looks like. This is a recently posted paper by Johan Chang. And what you see is that at 0 Tesla, there's nothing. And at 16.5 Tesla, there's a very sharp charge ordering peak. Now,
Can you tell us what the peak intensity means in this case?
no, I can't.
I mean, it doesn't make any sense to me unless you're seeing a change in the range of the order.
So let me come back to that later, but my lack of understanding of the intensity of this peak is extremely deep. I really don't understand it from very many angles. But let me focus on the things I do understand. So what you see is that this is a very sharp peak. This corresponds to a correlation length of, I can't remember, it's a couple of hundred angstroms in plane. So that's the first thing. It's a very sharp peak. You don't have to do any background subtraction to see it. It's really there. The other thing that they really tried hard to make go away but couldn't is that this peak occurs in one in-plane direction but not in the other. So this is a unidirectional charge density wave. It's modulation in one direction. It's, if you want, a smectic phase of this material. And the other thing is that this is a scan in the interplane direction. So this is the scan in the interplane direction. All of the charge density wave things that have been looked at previously, this short range stuff, corresponds to rods of scattering, which means that there's essentially no correlations in the third direction. This high field charge density wave is really order. It's a Bragg, well, it's a finite width, but it's a Braggish peak. It corresponds to correlation lengths of at least 50 angstroms in the interplane direction as well. So the correlation volume of this is orders of magnitude bigger than anything that's been seen previously. So we really know what's going on here. We're getting unidirectional charge density wave order when we suppress superconductivity.
Is it aligned with, by the chains or perpendicular?
The ordering vector goes along the chain direction. So the stripes are perpendicular to the chains. I should say this three-dimensional ordering was discovered actually using pulsed fields by my colleagues at SLAC, but this beautiful detailed study could only be done in static fields, so that was first, this unidirectionality was first discovered in this paper by Johan Chang. My colleagues at SLAC, and this is unpublished 2-week-old data that nobody else in the world knows about, so you're among the first people to hear about this, that this same sort of structure has first been shown to persist up to the highest fields that they can reach in the pulsed fields experiment, which is 32 Tesla. So this is over a broad range of fields, and also now over a range of doping. At this lower doping, the critical field is 23 Tesla, so inaccessible to static field measurements. So this is really a feature of a regime of the phase diagram.
How is the field applied relative to
In the C direction, perpendicular to the copper oxide planes, to the conducting planes. Here's the phase diagram from this Johan Chang paper. Here's magnetic field, here's temperature. The data I showed you with the charge ordering peak rowing and then shrinking as you went down was taking a line along this cut. Here's a cut at the zero field superconducting TC, and what you see is the three-dimensional, when you've suppressed superconductivity, the three-dimensional charge density wave ordering temperature coincides with what the superconducting TC was in zero field. Okay, you know, again, this is extraordinarily non-generic. You would have thought this was enormously fine-tuned. So there's really something to be explained here. We can do the other thing. I showed you that if I suppress superconductivity, I enhance the charge density wave. For reasons that I don't understand, it seems that even modest pressures at zero field tend to suppress the charge density wave. There's not actually direct evidence of this. This is inferred from transport, but it's probably correct. And so here, this blue is the superconducting phase boundary at zero pressure. When enough pressure is applied to suppress the charge density wave, the superconducting TC is significantly enhanced. So these are in really delicate balance with each other. Just tip the balance one way or another, and the one or the other order wins. I did want to say that these complex phase diagrams with many orders on similar scales is not unique to the Cuprates. This is one of Paul's favorite families of materials, and in fact, if anything, the phase diagram is more complex here. And that's even without all the interesting field-induced phases.
Unfortunately, it's a 1 degree thing.
What?
Unfortunately, the TC is 1 degree instead of 100.
They're the same.
Yes.
I'm a theoretical physicist. Okay, so good. So I'm not going to get to much of the theory. That's probably okay. What gives rise to this complexity of these phase diagrams? Well, maybe there is some amount of fine-tuning going on. After all, these are materials that have been selected for some interesting property, in particular for high-temperature superconductivity. And so maybe by selecting for high-temperature superconductivity, we've unwittingly tuned ourselves close to some horrible multicritical point. No, some wonderful multicritical point. And in particular, there are, I mean, if you study model problems and you study TC as a function of interactions, you always find that TC is optimized for intermediate coupling. If the interactions are strong, you get an insulator. If the interactions are weak, you just get a metal, and superconductivity occurs always when the interactions are comparable to the bandwidth. So maybe that's true, and maybe we should think about this as some form of quantum frustration, that the interactions want states that are eigenstates of position, and the kinetic energy wants states that are eigenstates of momentum, and we're tuning ourselves when we talk about highly correlated systems. What we mean is that neither of these is dominant, and so maybe that's the tuning involved. I mean, in fact, that's sort of definitionally what we mean by highly correlated electrons, is that we're in a fluid state, but in which the interaction effects are strong. Okay, I'm going to skip all the theory because I've run out of time. Okay, I promised I would define what an electron nematic is. Okay, so I want to make an analogy. We could get complex phase diagrams in classical liquid crystals. We can sort of think of these various liquid crystal phases as being partially melted versions of an underlying broken symmetry state, which is a crystal. So I would like to imagine something similar for a correlated electron system, where over here, where the interactions are dominant, you have some complicated electron crystal. Over here, you have the familiar Fermi gas. And then if you imagine looking at states of correlated systems by sequentially melting the crystal, you might be able to understand the occurrence of a complex phase diagram. Again, looking at not as how are the symmetries broken as you lower the temperature or decrease the amount of quantum fluctuations, but looking at how the symmetries are sequentially restored as you increase the temperature or increase the quantum fluctuations. And so, in particular, nematic order would be the most primitive of these. A nematic classical liquid crystal is a state that breaks rotational symmetry but preserves all the other symmetries. In particular, preserves translation symmetry. So an electron nematic state would be a state that preserves the crystal translation symmetries, that is to say the symmetries, I mean, everything's living in a crystal, so the translation symmetry of the crystal, but breaks the, quote, rotational symmetries, which in this case means the point group symmetries of the crystal. Okay, and I'm going to skip to the end and not do any of the theory. That's pretty.
What was that?
That's STM. That's a picture of something as a function of position. And so
The same could be said about any picture, though.
No, but it's particularly true of STM.
Oh.
I mean, I can tell you what it is. It's a Z-map. It's the picture of the dIdV at positive energy divided by dIdV at negative energy at some particular energy as a function of position. Good. So I hope I've convinced you that the mechanism of high temperature superconductivity is understood and why it has to do with magnetism. I hope I've convinced you that the question of the complexity of the phase diagram is an interesting problem. I have not told you anything about how to understand the normal or bad metal state, and I haven't told you anything about exotic phases. Both of these are decidedly unsolved problems, although in both these cases there's really promising and exciting developments in the last year or two. So, thank you.
I have a
struggling with the mechanism. So since you brought up the Kohn-Luttinger
Yeah.
mechanism, over there I could still think of some sort of attraction due to, one loop diagram in which
Right.
The quasi-particles participate and
Yes.
provide some, long-range peace.
Yes.
But you said here it's always repulsion, never attraction. Is there some effective attraction in the
So, no, I mean, it really is always repulsive. V is a positive number. I mean, it depends what you mean.
Let's say in the coordinate space. I take your V, translate the coordinate space. Is there a piece that changes sign or?
It can. That's what Kohn and Luttinger focused on, but that turns out not to be important in general. There's not a universal answer to that, but I think the real statement is that when you're looking, I mean, if you're willing to play by my rules, that is to say, this is a weak coupling theory. If we look at a weak coupling theory, we really are forced to look in K-space. The Fermi surface is the fundamental quantity, the fundamental organizing principle. And, unlike there's no real space way of coarse graining down to a Fermi surface. So this is why the theory of metallic critical phenomena is a mess. There's really, if you need to organize things around a Fermi surface, any way you think in real space is extraordinarily non-local, because the Fermi surface is a very non-local quantity. And so trying to look in real space at how these ripples go is, I think, misleading in this problem. You really want to look at it in K-space. Yeah.
Yes, in the abstract of the paper you mentioned that string theory have been employed in this endeavor.
Yes.
And also quantum information theory.
Yeah.
Could you briefly comment on that?
Sure. So, so first place, string theory. So this normal state that we have, what we really know well is what it isn't. It's really not describable by weakly interacting quasiparticles. Now, the problem is that when we look in our book of paradigmatic systems that we understand, that we can compare even loosely to things, unfortunately, that's where our book ends. We don't have other examples. We have, in one dimension, Luttinger liquids. So various people have tried to make analogies between this and one-dimensional Luttinger liquids. But one dimension, 1 + 1 dimensions to you, is very special. So we're desperate enough that we're willing to turn to holography. And holographically, people are able to say, listen, I've got for you the solution of some strongly interacting field theory. I unfortunately don't know quite what the field theory is, but I promise you this is the solution. And moreover, it's strongly interacting, so it doesn't have quasiparticles. So can we look and try to understand, can we try to see things that are familiar here? Now, if we do, what do we learn? Well, it's not obvious. It depends on how optimistic you are. If you're very optimistic, you might say, we have a holographic theory of bad metals. If you're less optimistic, you say, okay, we have a holographic theory of something that looks like bad metals. Let's now try to analyze that theory using more conventional methods. And once we understand that, knowing what the answer had to be, now let's try to apply that to models that are more directly relevant to our materials. So among that group of authors, there's not agreement on which of these roles would be best for holography, but we really are desperate on this problem.
Phenomenologically, these holographic theories are effective in quantum Are they basically zero temperature fixed points?
So they're often unstable fixed points. They're conformal field theories. They're probably often unstable. So you might imagine, though, that they control some intermediate asymptotics of some problem. So information theory. So again, there isn't complete agreement, but what I meant by that is that there are now really exciting new methods, non-perturbative methods for trying to study paradigmatic model problems numerically of strongly interacting systems using constructions from quantum information theory. Things like tensor product states and mirrors, and these various things have been leading both to constructions of model states and to new ways of getting more and more accurate numerical studies so that we can say, I mean, you know, the Hubbard model behaves in such and such a way. Then we can negotiate about what the Hubbard model has to do with the Cuprates, but at least we're not in the dark on what we're talking about. So it both provides a possible method for solution and for understanding some of these solutions in more, you know, it gives us better wave functions than just Hartree-Fock wave functions. So those are the...
Well, I don't know whether it has anything to do with it, but about 20 years ago or so, there was a McLaughlin wave function with fractional charges or something.
Yeah.
Did anything come up with that theory?
So first place, that theory is the theory of the fractional quantum Hall effect. It's certainly correct. The Laughlin theory is in the class of theories of exotic phases playing a role. I think there are good reasons to think that the particular exotic phase that he proposed is not relevant here. It involves time reversal symmetry breaking in a way that's been pretty much ruled out by experiment. But the idea that there are exotic fractionalized phases that are cousins of that may play a role is actually very much alive and well. And where the big progress is made is we certainly know model problems for which these are the right answer. Okay? Whether they're relevant to experiment, they're now respectable theoretical physics.
Okay, let's thank Steve again.